Hi again, welcome to this part of Chemical Thermodynamics lecture series. In this session, we will discuss internal energy and the first law of thermodynamics. Internal energy is defined as the total energy of a given system. Energy is the capacity of the system to do work, and internal energy represents the net energy content of the system. It includes both kinetic and potential energies. Kinetic energy of to molecular motions, whereas potential energies arise from charge interactions and position of molecules within the system. Consider you've got a system which is defined by a set of thermodynamic variables in the initial state, and during a process along this pathway it changes to final conditions with new set of thermodynamic variables. During this process, as the thermodynamic variables change, you have a change in internal energy also occurring, and that change in internal energy during the process can be defined by the difference in internal energies at the respective states. That is, it is a state function defined by state variables, and internal energy is an extensive property. That is, the amount of internal energy depends on the amount of substance present inside the system. Whereas the molar internal energy per mole of the substance is independent of the amount of substance, that is, it is an intensive property. With this background, we move on to molecular level interpretation of internal energy. Molecules are provided with certain possibilities of movement, different modes of movement are possible. They are called motional degrees of freedom. For example, molecules may undergo translational motion from one place or one position in the three-dimensional geometry to another position like this. Or there can be rotational motion about a particular axis, or vibrational motion, that the bones are vibrating, stretching and elongating like this. All these three motions contribute to energy of the molecule, and these motions are reflected in most of the molecular properties. For example, when high amount of energy is focused on bond length, on vibration of bonds, what happens is the bond vibration occurs like this, and at a certain moment bond dissociation occurs. The bond breaks because huge amount of energy is concentrated on the bond. Like this, all the three motions contribute to energy of the molecule, that is to the internal energy of the system, as well as the internal structure of molecules, the organization of atoms and interaction of atoms between each other within the molecular structure also contribute to net energy or the internal energy of the system. Consider you have got absolute zero temperature, where the assumption is that all the three modes of motion, that is the rotational, vibrational and translational motion, are absent, and in that condition only the internal structure of the molecule or the organization of atoms within the molecules contributes to the energy of the molecule. And that internal energy, that molar internal energy, is defined by Um at 0. And now you have got higher temperature where the three modes of motion are executing. So the molar internal energy is a contribution of all the three motions and the internal structure. That is, then the molar internal energy at this temperature T is contributed by internal structure of the molecule as in absolute zero, and with a motional contribution in addition to that. And this motional contribution, you can see from statistical analysis that it is given by or expressed by phi by 2 RT, with this expression for linear molecules and as 3 RT for non-linear molecule. T is the temperature and R is the universal gas constant. Whatever it is, you can see that whether the linear or non-linear molecule, it is clear the internal energy at a given temperature is dependent on temperature of the system. Or in short, internal energy is temperature dependent. Okay, at this point, there may be a question that what about volume dependence? The idea is that for an ideal gas where intermolecular interactions are postulated to be or assumed to be absent, the volume has no significant role. That is why internal energy is independent of volume exclusively for ideal gases, because there is no intermolecular interaction between molecules for an ideal gas. Okay. Now we will move on to the first law of thermodynamics, which is based on the concept of internal energy, work and heat. We have seen all these three before. We have seen that work and heat are two equivalent ways of changing energy, and now we can say changing internal energy. We'll see how it happens. This is our system defined by the internal energy at its initial state by Ui like this, and suppose this system is moving to a new set of thermodynamic state with a new internal energy Uf during a process. During that process, there can be two consequences, either in terms of heat or in terms of work. Suppose the system gives out heat like this, then what happens is the surrounding molecules can move more vigorously. That is, for example, an ice in the surroundings can be molten as the system gives out energy. Likewise, the system can perform work also. It can lift a weight from there to here. So these are the two possibilities or two modes of exchanging energy from the system to the surroundings during a process. And that is how you meet a new internal energy. And energy transfer occurs as heat or as work. And the difference in internal energy during the process is given by delta U, and it can be seen that energy storage in the form of internal energy, and that energy change, internal energy change, can be expressed from this as a sum of heat and work. This is the mathematical form of first law of thermodynamics, that is, change in internal energy accompanied in a process can be expressed as a combination of heat and work associated in that process. Or you can say energy transfer occurs in the form of heat and work, whereas energy storage occurs in the form of internal energy. Now, considering a system exclusively an isolated system, for an isolated system, you know by definition it does not exchange energy and matter with the surroundings. In that case, the net internal energy remains constant. That is the statement of first law of thermodynamics. For an isolated system, as it does not exchange energy with the surroundings, that means two modes of energy exchange are heat and work. There is no energy exchange by isolating the system, that means heat and work are zero. That leads to the change in internal energy to be zero. That is, internal energy remains constant in an isolated system. That is the statement of first law of thermodynamics. And this first law can be demonstrated with the help of considering a perpetual motion machine. We know what is a perpetual motion machine. A machine which does not need additional energy input from the surroundings. It works for infinite duration with the very initial supplement of energy like this. It continues to rotate. It continues to work. So this is not possible because once you give the energy, this machine is giving out work for indefinite period. This cannot happen because in order to the work to be happening, you need to have energy from somewhere according to first law. And that is why the perpetual motion machine is not a realistic one. Okay, and this impossibility of the perpetual motion machine fully demonstrates the first law of thermodynamics. Now we will move on to a particular case. We will restrict our system to be isochoric. Isochoric means the volume change is zero, or a process, a system undergoes process keeping the volume constant. That is isochoric process. With this definition of internal energy, we will see work. Work has got two considerations. So far we have been discussing about only expansion work, but work actually involves in a chemical system, for example, an expansion work as well as a non-expansion work. Non-expansion work can be demonstrated with a very simple example, very highly simplified example is what I am showing here. Suppose you are putting a molecule of sodium chloride or a solute inside of water. What happens is the molecule undergo dissociation and move apart by absorbing energy from the surroundings. This is what we observe in the end. So what are the works involved in this? In the beginning, the bonds between the molecule break, that is dissociation occurs, that is a known expansion work, the breakage of the bond, and the ions move far apart from each other. There is a volume change, there is kind of expansion work associated there. So these are the two works occurring in this process, that is an expansion work a non-expansion work. Here the bond breakage, and an expansion work, that is the ions are moving away from each other, needing more volume to occupy. With this background of expansion and non-expansion work, now we can see what happens in an isochoric process. Now we define our system to be isochoric, and it is incapable of doing non-expansion work, assuming that there is no non-expansion work, no chemical reaction, no production of energy, no breakage of bond. Being an isochoric system, the change in volume is zero, that is the expansion work, that is the pressure volume work now becomes zero. So work of expansion is zero. And defining it to be incapable of non-expansion work, the second part of work is also a zero. In that condition, we can write the total work as a zero, so the change in internal energy is represented by the heat. So whatever heat is absorbed by the system is stored as internal energy, or whatever heat is lost by the system is reflected in the loss in internal energy at constant volume. So this relation holds, that is change in internal energy is equal to the heat in constant volume conditions. Taking it further, we can see internal energy is a function of temperature and volume for non-ideal gas. We have seen before that for ideal gas, volume consideration is insignificant and it is only temperature dependent. But for non-ideal or real gases, internal energy is both temperature and volume dependent. So an infinitesimally small change in internal energy occurring in a small step of a process can be given by du as derivative of this function with respect to both temperature and volume. That is, here you can use the help of a partial derivatization, that is partial derivative of internal energy with respect to temperature at constant volume, summed up by partial derivative of internal energy with respect to volume but at constant temperature. This will give the small or infinitesimally small change in internal energy occurring in a given infinitesimally small part of the process. Defining the process to be isochoric, that is, there is no change in volume. As there is no change in volume, we don't need to consider the second part of the differential. Then you can see the change in internal energy depends only on change in temperature, or there is a factor that change in internal energy with respect to change in temperature at a constant volume. That factor is defined to be heat capacity at constant volume, denoted by Cv with a suffix. So, if you go for a difference in internal energy with respect to a change in temperature at constant volume, that will give you heat capacity. We will see the real meaning of heat capacity in the upcoming slide. You can obtain that the small change in internal energy can be written as a product of change in temperature and heat capacity of the system, and to a measurable change, delta U, the change in internal energy during the whole process, can be expressed as the change in temperature during the process multiplied by the heat capacity of the system. To see what is really heat capacity, as we say, it is an isochoric process, that is, there is no pressure volume work. The work is zero. And according to first law, as work is zero, the internal energy change become heat, equivalent to heat at constant volume. So you can write heat at constant volume as the product of temperature difference and heat capacity, and rearranging this, heat capacity can be given as a ratio of heat at constant volume to the temperature difference. That is, heat required to cause a particular temperature difference. That is the explanation of or the meaning of heat capacity. Suppose you are causing a temperature difference of unity. Suppose you are giving Q amount of heat to the system and temperature changes by 1 unit. Then that amount of heat is called heat capacity. The heat required to raise the temperature of a system by 1 degree centigrade. That is heat capacity. So heat capacity is the capacity of the system to hold heat, or by absorbing what amount of heat its temperature changes. That is what is reflected in heat capacity. And with this definition of heat capacity, we can stop here, and in the next session we will see a new concept called enthalpy and continue a new definition of heat capacity, or heat capacity at a different condition of constant pressure. Okay. With that, this session is closing, and see you with the enthalpy session next time.